Swayam Prabha. Digital India. Educated India.
Now I am going to provide you a very broad introduction to the Bayesian estimation. So least square estimation, maximum likelihood estimation, Bayesian estimation. Bayesian techniques are very fundamental. In AI we talk about Bayesian networks. Everything depends on the basic aspects of Bayes' rule. Bayes' rule I have already introduced you when I talked about the general estimation techniques. So I am now going to redo the Bayesian framework. So x is a n vector which is unknown. Please understand the starting point of any Bayesian, the unknown is a random variable. If unknown is a random variable, I am supposed to have some probabilistic information about the prior. So Px is the prior distribution of x. That's a known knowledge with which I am coming into the play. Then I conduct the experiment, Z comes out. Z has information about x, is a conditional distribution. X hat is equal to a function phi of Z. You remember, phi is the estimator. The estimator is a function of the observation. The output is the estimate. So this is the random variable is the estimate, both are random, so that's the error. So instead of calling residual, I am calling the error. This is the error in the estimate. Now please understand, the error in the estimate of the random variable. So what is x? X has a prior distribution. Mother Nature picks a value of x based on the distribution P of x. So today it may take one value, tomorrow it may take another value. If you repeat it, the value of the prior x may vary because the Mother Nature is trying to tease us by picking x from a prior distribution. At least that's the approach we take, and that's the role of prior. The error in the estimate is x minus x hat. Now I am going to create a cost function which is the cost of associating the estimate with the truth. So the cost of the estimate is equal to, is a function of the error. So the cost is a functional which is from Rn to R. So cost is defined by C of x tilde. X tilde is the error. This is the cost associated with the error in the estimate. Cost associated with the error in the estimate. Please understand, the cost is always must be a scalar valued function of a vector because I want to be able to have a uni-objective minimization. I want to minimize the cost. Please understand, in all these problems we are interested in reformulating as one of minimizing the cost. In economics, they often formulate it as maximization of profit. Both are equivalent ways of doing it. Now, if I want to be able to have a cost function, what are the desirable properties of the cost function? Please understand, in the case of least square, there is a cost. What is the cost function? That is f of x. And what is the f of x? Which is z minus h f transpose minus z minus h of x. The sum of squared errors was the cost function in least squares. We minimized it. In the case of maximum likelihood, I want to be able to maximize the likelihood with respect to the parameter x, given the distribution, the conditional distribution function. So in one case, it was the minimization of the cost in the case of least square. In the case of maximal likelihood, it is maximizing the probability function with respect to the parameter given z. Here, I am working in yet another framework. I have unknown x is random. Mother Nature picks a value of the unknown random from the distribution. In my experiment, the observations are going to be controlled by the value that Mother Nature picked but did not tell us. So Pz of x is the conditional distribution, x hat is the estimate, and I am associating a cost function with the error in the estimate. The properties of the cost function is such that if the error is 0, the cost must be 0, which makes a lot of sense. And the cost function must be monotonically increasing. For example, if A is the vector, B is the vector, if the size of A is less than the size of B, the cost at A must be less than or equal to cost at B. That means vectors, error vectors with a larger norm must have larger cost than error vectors with a smaller norm. So A and B are the values of the error vectors. If the norm of the error vector A is less than the norm of the error vector B, the cost associated with A must be less than or equal to the cost associated with B. That means cost function is monotonic on the space of norms of the error vectors, because the errors are vectors. I want to be able to associate a scalar with the vector, so I am talking about the norm. So C of A must be equal to C of less than or equal to C of B if the norm of A, if the norm of A is less than or equal to the norm of B. So what are the examples of cost function? One is called the sum of squared errors. That's similar to the least squares. Error square, sum of squared errors. So this is equivalent to the least square cost function. And so Cx hat, the cost associated with the estimate x hat is equal to x minus x hat. Please understand, x tilde is equal to x minus x hat. So cost associated with the error is equal to the inner product of the error vector with itself. Then I can have weighted least square estimate. So that is the weight matrix. So x hat transpose w x hat, x tilde transpose w x tilde, which is x minus x hat transpose w x minus x hat. Now please remember, this looks like z minus h of x transpose equal to z minus h of x. This results z minus h of x transpose R inverse z minus h of x. So mathematically there are parallelism, but conceptually there are differences. So this is the energy norm of the error with respect to the matrix W. Then there is another choice which is called the uniform cost. What does it mean? The cost is like this, the cost function. If the error, if x tilde, this should be x tilde, sorry. If the norm of the error x tilde is less than or equal to minus epsilon plus epsilon, lies in this range, the cost is 0. With me? Outside of it, the cost is 1. Outside of it, the cost is 1. Outside of this, is cost is 1. So that is the called uniform cost. That means if the error is very small, the cost is 0. Otherwise, the cost is constant to be equal to 1. Then when x is a scalar, I can also measure the cost as an absolute value. So C of x tilde is equal to absolute value of x minus x tilde. So the x tilde is the error, this is the estimate. So this is the absolute value of the difference between the truth and the estimate. These are at least 4 different choices. These are not the only choices, there are other choices possible. So every Bayesian estimation associated with the prior, the conditional distribution, and the cost function, and the Bayes rule. So there are lots of actors in this game. How do I utilize all these actors to be able to derive what I want? So examples of cost function, any cost function which is symmetric and convex. Symmetry means what? The cost function for x tilde must be equal to the cost function for minus x tilde. That means the cost function is independent of the sign of the error. It only depends on the magnitude of the error. And the cost function must be convex. So if x is an error, y is an error, ax plus 1 minus ay is this is the x, this is the y. So this point is a times, this is a times x plus 1 minus a times y. Then I can compute the cost in here. So this is Cx. So this value is a times Cx plus 1 minus a times C of y. This value is equal to, if I consider this value as z, this is equal to C of z. So there is a difference between the two. There is a difference between the two. So this value is less than that. That means the function value is below the chord, where a is less than or between 0 and 1. That's the definition of convexity. So in general, one way to choose the cost function is that it is symmetric. That means the value is independent of the sign. What is a function that is symmetric? Y is equal to x squared is a symmetric function. Y is equal to x squared is a symmetric function. X minus x minus x, x is a symmetric function. Is also convex. So quadratic cost functions satisfy symmetry and convexity very easily. So we can use convex quadratic function as the cost function for Bayes estimation. So we are all the players are in place. So we are going to formulate the problem. P of x is the prior, Pz of x is the conditional distribution, Z is the observation that is already obtained, I have the sample, C is the cost function, I have already chosen the cost function. So the choice of the cost function, I already talked about, there are at least 4 different choices. The general rule is the cost function will be symmetric and convex. So I have the prior, I have the conditional distribution, I have the actual observation from the conditional distribution, and I have chosen the cost function. The goal is to minimize the base cost. So what is base cost? The base cost is associated with the estimate x hat. So B of x hat is the cost associated with the Bayesian estimate x hat. And how is that defined? That is equal to expected value of C of x tilde. What is x tilde? X tilde is equal to x minus x hat. And what is the expected value? Please understand, x is random and z is random. That's the Bayesian rule. X is random, z is random. So x has a distribution, z has a distribution. So pxy is called the joint distribution. So I have to integrate this by multiplying the cost function by the joint distribution and integrate it with respect to x and z. Please remember, z is a m variable, x is a n variable. So this is the double integral of the cost function multiplied by the joint distribution with respect to the variable x and variable z. So this is the general statement of the base cost function. Now, the joint distribution can be expressed as the product of the conditional distribution and p of x. It can also express this way: p given x, x given z and pz. This comes from the basic Bayes rule. Now I am going to re-express this Bx hat is equal to Rm over Bxz divided Bz dz, where Bx hat z. Bx hat z means what? Given the observation, what is the distribution, what is the cost of the estimate? And that is given by this inner integral. So what is it I am trying to do? I am trying to substitute for this the product. I am trying to substitute for this the product this way. So let me erase all the other parts. So this is the conditional, this is joint density, this is the breakup of that. I am going to substitute this in here. So if I substituted Pxz by this, I can split this integral into two parts. One with respect to the conditional density given z, another is Pz, you can readily see. Therefore, this Bx is given by these two. This is the inner integral, this is the outer integral. So this is equivalent to the Bayes rule, Bayes cost function. I want to be able to minimize this this. But I want to look at this. What is this? It is this cost multiplied by the probability distribution of Pz. If I am going to multiply the distribution of Pz, what is this? This is looking like. What is the average value of x? The average of x is equal to integral over r x px dx. So you already know px dx. So this looks like the average of b of x hat given z pz, and that is given by this. Therefore, p of z is always greater than or equal to 0, the probability of observing certain set of observation. So minimizing b of x hat is equivalent to minimizing the inner integrand, which is b of x hat given z. So by minimizing this, I can minimize this. Therefore, I reduce the problem of minimizing the Bayesian cost function to one of minimizing this conditional Bayes cost function. So what is this? Let us say it in words. This is the Bayesian cost of the estimate x hat given the observation. So minimizing this quantity minimizes the whole quantity. My aim is to be able to minimize the whole quantity. So I am simplifying the problem by analyzing the structure of the Bayes cost function. So I now move on to characterizing the properties of this conditional cost function. What is the conditional cost function? What is the Bayesian cost associated with the estimate x hat given the observation z? Given the observation z. So that's the idea. Now I'm going to consider the special cases, which is called Bayesian least squares. Please understand, we already have talked about least squares. Those least squares are coming from Gauss. So Gaussian least squares, Gaussian unweighted, Gaussian weighted. But this framework of Bayesian also can give rise to least squares. Why? You must have already guessed it. I want the Bayesian cost function to be symmetric and convex. An example of a Bayesian symmetric convex function is sum of squared errors, weighted sum, unweighted sum, uniform cost. So we have already talked about lots of cost functions. Now I'm going to concentrate on quadratic cost functions. So I'm going to be talking about Bayes least squares estimation, least square within the context of Bayesian theory. So mu is called the conditional mean. Mu is equal to expected value of x given z. Expected value of given z is given by x times the conditional probability of x given z. That comes from the definition of conditional expectation. So given z means is a function of z. Therefore, this mu estimation is a function of the noisy observation z. I'm now going to choose my cost function to be x minus x hat transpose w x minus x hat, weighted sum of squared errors. So bx hat, the total Bayesian cost, is equal to expected value of the cost associated with the error. X tilde is the error. X tilde is equal to x minus x hat. So substituting this becomes the expected value of this. Now I'm going to add and subtract mu to both the terms. I'm going to multiply this out. So this is one term, this is another term, this is one term, this is another term. You will get 4 terms. 2 of the 4 terms are equal, so I get only 3 terms with a factor 2. We have done these things several times. Now I am going to manipulate this cross term. So look at this now. That's a cross term, x minus mu transpose w mu minus x hat. So that is a iterated law of conditional expectation. So by the iterated law of conditional expectation, what is it I can do? I can compute the expectation given z, and then I can recompute the expectation with respect to z. That means expected value of x is equal to expected value of x given z. So this is with respect to z. This is with respect to x. This is called iterated conditional expectation. So this can be written as the iterated form of conditional expectation. So this is the one which is conditional expectation. So I consider the internal iterated expectation, which is x minus mu transpose w x minus mu minus x transpose z. Now please understand, x hat is a function of z. If z is given, I already know this. So mu minus x hat is a constant. I can take it out of the expectation. W is also known. In here I am utilizing the following fact: x minus mu transpose w mu minus x hat is also can be written as mu minus x hat transpose w transpose is w because w is symmetric. That's equal to x minus mu. So using this formulation, mu minus x hat comes out, w comes out. I'm left with this. So this is equal to mu minus x hat transpose w. If I substitute the expectation, expected value of x given z minus mu. Now let's go back to the definition of mu. Mu is equal to expected value of x given mu. So these two are same. So that is 0. So the cross term is 0. So by using the iterated law of conditional expectation, I can make sure that this cross term is 0. So I'm left with only 2 terms. So the bx hat, please go back. The bx hat, sum of 3 terms, 1 term is 0. So I'm left with 2 terms. So that is equal to this term plus this term. Now the only control I have is choice of x hat. So x hat is the only estimate. Now please understand, there are 2 terms. What is the only variable I have? I can change my estimate. So x hat is the only control I have. So by changing x hat, I can only affect this. I cannot affect the first term. Therefore, I can make this sum minimum by the choice of x star that makes the second term 0. Please understand, this is the positive definite quadratic form. This is the positive definite quadratic form, expected values of that. So first term I cannot control because mu is already fixed, x is already fixed. X is already given by the prior distribution, w is known. So the only control I have is x hat. So if I chose x hat to be equal to mu, then the last term becomes 0. And what is x hat is equal to mu? This is called the posterior mean. Please look at that now. X hat is equal to expected value of x given z. So this is the expected value of x given z. That's called the posterior mean. That's called the posterior mean. Therefore, the Bayesian mean square estimate, which is the x hat ms, please understand we are trying to Bayesian least squares, is the conditional mean. The conditional mean expression is given by this. It can also be given by this. I am simply expressing the conditional density. The conditional density, so what is this? This is expected value of x given the expected value of x given p of x given z dz. I'm sorry, p of x given z d, this is dx, but p of x given d by the Bayes rule can be written like this. You already know that. You already know that. And that expression can be rewritten like this. Therefore, what's the conclusion? The best estimate that minimizes the Bayesian cost is the posterior mean. Is the posterior mean. Is the posterior mean. What is the posterior mean? So let's go back to the Bayes rule. The posterior xz is equal to, this is zx given by pz. This is the Bayes rule. So this is prior, this is posterior, this is the conditional distribution. So you compute this, you compute the posterior distribution, the expected value of this posterior distribution is the best estimate under the quadratic loss function under the Bayesian framework. So this is what's called best mean square estimate, the best mean square estimate under the Bayesian setup. So we have combined Bayes and the least squares to be able to get at this formula. We started a study of Bayes least squares estimation. We showed that under the quadratic cost as a cost function, the conditional expectation, which is the conditional mean of the posterior density function, is the optimal estimate. We proved this by contents of slide 6, slide 7, and we now express bx hat. X hat is the estimate. Bx hat has two components as given in this slide, the top equation. We have only one control, x hat. So there are two terms. The first term doesn't depend on x hat. The second term depends on x hat. So the only way I can change anything is by manipulating the second term. So by choosing x hat is equal to mu is equal to the conditional mean of x given z, which is the posterior mean. We have now come to conclude that the best mean square estimate in the Bayesian sense is essentially the posterior mean, which is the conditional mean, and which is given by the equation at the bottom of the slide 8. This is where we stopped in the last class. Now we are going to continue to analyze further the properties of Bayes least squares. So first we are going to show the Bayes mean square estimate. Bayes least squares estimate, you can think of it in weighted least squares estimate, you can think of it in several ways, is unbiased. So to prove that, consider the difference between x and its mean square estimate. We have already used the notion of iterated conditional expectations. So this outer conditional is with respect to z, and given z, XMS, the mean square estimate inherits the randomness. So the first one is with respect to the randomness conditioned on z. The second outer expectation is going to compute the expectation with respect to the distribution of z. So if I now evaluate this conditional expectation, the first one is expected value of x given z. The second one is already a conditional expectation. So expectation of expectation is itself. So these two are equal. Therefore, the inside quantity is 0. Therefore, the expectation is 0. That means the mean square estimate obtained using the Bayesian formulation is unbiased. Now, the mean square error is equal to x minus x hat ms. X hat ms is the mean square estimate. The actual value minus estimate is the error. That implies the expected value of the error is also equal to 0, because we just showed that the estimate is unbiased. The mean of the error is 0. Mean of the error is 0. Now, I would like to be able to compute the total variance in the component of the vector x. So there are two things. If I have a vector x, let's suppose I have a random variable x, I can talk about the covariance of x, which is the matrix. I can also talk about the total variance of x. The total variance of x is equal to sum of the variance of the individual components of x, and that's also equal to the trace of the covariance matrix of x. Okay, that is the basic property. That's the basic property. So the total variance of the components of x, I'm going to compute this as a inner product, which is x hat minus x hat ms. No, this must be x, sorry, this must be x minus x hat ms, so there's no hat here. X minus x hat ms transpose x minus x hat, it is an inner product. I am going to now multiply by the conditional distribution of x given z. Dx, I am assuming w is identity, which is the weights are equal and equal to 1. So this is the total variance. Since x hat ms minimizes bx hat z, x hat ms also minimizes the variance of this estimate. The variance of this estimate. I want you to be able to relate these things. That's how the Bayesian formulation come into being. Go back to the basic Bayesian formulation. If you went back to slide 5, you can really see this equation bx hat is the integral of bx hat z pz dz. So if I minimize this, I minimize the whole integral, and that's the idea that's used repeatedly here. Now I would like to be able to bring about the similarity. Using Gauss-Markov theorem, when we had only observation, no prior, we saw x hat ls is a blue. The least square estimate has lots of desired property, is a blue. And we proved Gauss-Markov theorem. Among all the linear unbiased estimate, the least square estimate has the best variance in the sense of least variance. That's the contents of Gauss-Markov theorem. But in the Bayesian setup, I have observation, I have prior. Please understand, on the left-hand side, the Fisher's framework. I have only observation. The right hand side, I have observation and prior. In this case, we formulated in the context of Bayesian. And what's common between the two? There are lots of little things common between the two. Here also, I used the cost function as the sum of squared errors. I could have used weighted sum of squared errors. Here on the right hand side, we used weighted sum of squared errors. So there is commonality in the cost function. The only difference is I have prior information, and that complicates the matter a little bit, the arithmetic a little bit. But that's where the Bayes rule comes into play. So by invoking the Bayes rule, we were able to show that the Bayes posterior conditional mean, this what is X hat MS? It is a posterior conditional mean, is a blue, is best linear unbiased estimate. Therefore, Bayes posterior mean square, Gauss-Markov theorem, these are two ways of attacking, formulating the statistical estimation problems, and there is a lot of undercurrent of similarity between the two, and that's what I wanted to emphasize in this. Now I'm going to work a couple of examples to be able to illustrate the Bayesian formulation. First, I'm going to work with a scalar case, then I'll work with a vector case. So X is a unknown, which is a scalar. X is a random variable. Let's assume X is a normal random variable with a mean mx and variance sigma square x. V is the observation error. Observation error has mean 0 and its own covariance sigma square v. So a random variable is affected by a random noise. The random noise is additive. So what is the problem? The problem is I have X may be a Gaussian random signal, V be the Gaussian observation noise. I'm considering two types of random variables. X is not observed by itself, X plus V is, so Z is the observation. I'm also going to make the standard assumption that X and V are uncorrelated, not incorrelated, uncorrelated. That means the cross covariance or the second moment between the two is 0. Now, I would like to be able to compute the distribution of Z. Here, I am going to use a standard theorem from probability theory. I am adding two random variables which are Gaussian. That is a fundamental result in probability theory. Sum of Gaussian is Gaussian. Sum of Gaussian random variable is Gaussian. Sum of Gaussian is Gaussian. And if the two random variables which are being added are uncorrelated, the mean of the sum is the sum of the means. So the mean of V is 0, the sum, the mean of X is Mx, so the total mean of Z is Mx. The variance of the sum is the sum of the variances if V and X are uncorrelated. So I'm using again some of the standard rules from probability theory. Sum of Gaussian is Gaussian. If the two Gaussian random variables are uncorrelated, the means add up, the variance add up. This is the simplest possible case. If X and V are correlated, there will be other correlation-based terms that will affect the variance. So I now know the distribution of Z, the observation. I want to be able to compute the conditional distribution Px given Z under the Bayesian framework. Now, Px is normal of mx sigma square. Given x, if you condition on x, pz of x is pc of x is normal x sigma v square. If x is given, I know there is no randomness associated with it. If x is given, the randomness in z is only because of v. So the mean of v is 0. So the mean of z given x is only x. X is given, it has no variance, because I am assuming that x is given to me. So the variance of z will be equal to sigma square v. So this is the conditional distribution of z given x. I hope you are all with me. This is the unconditional distribution of z. This is the unconditional distribution. This is the conditional distribution. The conditional distribution is given by this. So my aim is to be able to compute the posterior distribution pxz. I now know pzx, I know px, I know pz. So by invoking to the base rule, p of x given z is equal to p of z given x times p of x given by pz. P of x given z is given by this, p of x is given by this, p of z is given by this. Please understand, I have already computed the distribution of p of x, the conditional distribution p of z given x. I have also contributed the distribution p of z, all using simple fact that z is equal to x plus v, x and v are Gaussian, they are uncorrelated. So simply based on this, I have all the information. I am able to express my posterior density as a ratio. The numerator has product of two Gaussian, the denominator is another Gaussian. Every Gaussian density, if you recall, there is a, so if I say p of x is Gaussian, if p of x is normal mx sigma square x, what does this mean? This is equal to 1 over square root of 2 pi sigma x exponential minus x minus mx whole square divided by 2 sigma square x. This is the formula that comes in. So every one of these, each of these will have a term that depends on a factor like that. 1 over 2 pi sigma x, sigma v, sigma square root of sigma square plus v square. So those are all constants. I'm going to talk about all the constants clubbed into one single constant called beta. If I'm left with, once I club all the things in one constant beta, I don't want to worry about that. I can now only deal with the exponential term. There's an exponential term from here, exponential term from here, exponential term from here. So there are 3 exponential terms. I hope you're all with me. The exponential term will have this structure. Substituting the exponential term for each of these things, I want you to verify that this is the expression for the conditional expectation. The posterior, I'm sorry, this is the posterior distribution. That's right. This is the expression for the posterior distribution. Posterior. Once the posterior distribution can be simplified, I can compute its mean, variance, and etc. So, what is the rest of the thing? I want to be able to simplify the exponent term. So, simplifying the term in the square brackets. So, look at this now. Sorry. These are the terms in the square bracket. There are 3 terms. Simplifying the terms in the square bracket, you have one term, you have second term, you have a third term. I am going to use the notion of what's called a perfect square. There's a lot of algebra involved in here. I'm not showing every algebra, but I'm going to tell you every little step. You can expand this. You can expand this. You can expand this. You can collect all the x squared term. You can collect all the 2x term. Then you can collect all the term that does not depend on x. If you did that, the resulting expression is x squared plus 1 over sigma square v plus 1 over sigma square x minus 2x times z over sigma square v plus mx over sigma square x plus the rest of the term that comes out of this. Because this is a function of x. This is going to be the distribution, the given z is going to be a function of x. So consider x squared plus x plus 1. I want to be able to express this as a perfect square. This can be written as x squared plus 2 times x times 1 by 2 plus 1 by 2 whole square plus 1 minus 1 by 2 square minus 1 by 2 square. The 1 comes in here. I added 1/2 square, I am subtracting that. X I am representing as 2 times x by 2. So this is equal to x square plus 2 times x into 1/2 plus 1 over 2 square plus 1 minus 1 by 2 square. This can be written as x plus 1/2 of whole square minus plus 1 minus 1 by 2 square. So this is called the method of perfecting the square. By applying a technique which is similar to this term, so this is like x squared term, 2x term, constant term, I can perfect the square. To that end, I am going to define 1 over sigma square e is equal to that. I am going to define a new quantity x hat ms divided by sigma square e, which is equal to z by sigma square v plus mx by sigma square x. If I define these two, the right hand side of 1 now can be expressed as a perfect square, which is 1 over sigma square e x square minus 2x x hat ms plus x hat ms square, and that is equal to 1 over sigma square e x minus x hat ms square whole square. That means I have expressed this term, the equation on the right hand side of 1, using the quantities, the transformation in 2 and 3. I have expressed this as a perfect square, much like I did the perfect square at the end, at the bottom of slide 12. At the bottom of slide 12. Now, please remember now, there is a beta here. I am going to express this. So, the whole expression now can be expressed as alpha times another constant, which you can compute very easily. That is equal to exponential of minus 1/2 of x minus x hat ms divided by sigma square e whole square. So this is the posterior density. If this is the posterior density, by definition, this is the posterior mean, this is the posterior variance. This is the posterior variance. So what is that we have shown? By simplifying the 3 terms, expressing as a perfect square, I'm able to express the perfect square in terms of sigma square e and x hat ms, and these are the 2 quantities I have defined in equation 2 and 3. Therefore, the posterior mean is Gaussian, whose mean is x hat ms, and whose variance is sigma square e. Therefore, from equation 3, I have an expression for x hat ms. X hat ms now is equivalent to, from equation 3, I am rewriting this. So sigma square e by sigma square x square mx, sigma square e by sigma square v z. So what does this tell you? These two are weighting functions. These are weights. What is mx? Mx is the mean of the prior. What is z? Z is the new observation. So what is it? We are now trying to see the mean square, the Bayesian mean square estimate is simply a linear combination of the prior mean and the observation. Prior mean and the observation. Prior mean and the observation. So let's go back and look at that now. So that's exactly 3, and 5 comes from 3. Now, which can be rewritten as this quantity, which can be rewritten as this quantity by substituting for sigma square e. Please remember, what is sigma square e? Sigma square e is equal to sigma square v plus sigma square x divided by the product of sigma square v and sigma square x coming from equation 2. So using 2 and 3, I get an expression for the estimate and its variance. So the crux of the matter is to be able to express it as a perfect square. Now, if I substitute for sigma square e and simplify, this is a linear combination of x and y. Now, if you look at the definition of these two quantities, you can see this is alpha, that is 1 minus alpha. So this is a convex combination. In fact, it's not only a linear combination, it's a convex combination. So what does the convex combination tell you? This is the mfx. Sorry. This is the mfx. This is z. My best estimate is alpha times mfx, 1 minus alpha times z. That means the estimate lies in the line segment joining mx and z. That's a geometric interpretation. That's a geometric interpretation. Yes, there's a little bit of an algebra involved in here. So what is the summary? The summary is, by simplifying, by substituting the expressions for the Gaussian, by simplifying and by transformation of variables, we can express the posterior density as an equation 4, using the exponent in equation 4. So the mean square estimate is given by 5, which can be rewritten as a convex combination of mx and z, which is a very natural and a beautiful interpretation. I can also rewrite this, the expression at the bottom of slide 13, which is 6, as follows. That's equal to mx. Please understand, I can add and subtract ms. So I can rewrite x hat ms in the bottom of the last equation 6 also as mx plus a weight function, a weighting term z minus mfx. So what is mfx? Mfx is called prior. What is z? The observation. What is z minus mfx? That's called innovation. Please understand, if you didn't have an observation, the only information you have is prior. When the observation comes in, I want to be able to find out what is the new information that the observation is going to provide on the top of the prior. So z minus mfx is the new additional information that I am going to get out of the observation on the top of what prior has already given me. So this is the old information. This is the new information, which is the difference between the observation and the prior. That's called the innovation. So the new estimate is equal to the old prior information plus a weighted fact, the innovation weighted by a gain term. This is called a gain or a weight function or a parameter, whatever you want to call it. In estimation literature, this is called Kalman gain. Kalman is one of the famous system theorists. He derived the expression for Kalman filtering in 1960. And there are multiple ways of deriving Kalman filters. So in a sense, we have essentially derived a simple expression for the Kalman filter based on the problem of trying to estimate x when we can observe only x plus v. Now there are important conclusions. Sigma square x is the prior variance, sigma square v is the variance of the noise. If sigma square x is greater than the noise variance, means what? The prior is less informative. I have already told you the reciprocal of the variance is information. If the variance is high, information is less. If the variance is low, information is high. So in this case, if sigma square x is more than sigma square v, observation error is more, has a lesser variance, more information. So I am going to give more weight to the observation. If sigma square x is less than that, I am going to give a larger weight to the prior. This is a very natural adaptive property. It's a very natural adaptive property. It's a very natural adaptive property. Therefore, I can rewrite these equations in several different ways. Going back to this equation 6, equation 6 can also be written as A times m of x. A is alpha. So instead of calling it, instead of calling it A, instead of calling it alpha, I'm calling it A. So xms is A times mx plus 1 minus alpha times 1 minus A times z. I can add and subtract m of x. So therefrom I get this relation. So what is that I'm talking about here? How do I convert the equation 6 to the form that is given in here? You add and subtract, you get this form. Therefore, the equation in the first line of slide 14 and the equation on the last line of slide 13 are one and the same. So, in summary, the first example is a simple example. Yes, there is algebra. I have shown you the major steps in the algebra. I would like you to verify. That's called, in signal processing, this is called extracting the signal, extracting the random signal from the random noise. Signal extraction. Bayesian formulation. So this is applicable in signal processing, in statistical deduction theory. All these things are rooted in Bayesian estimation. Now I am going to consider the vector case. Z is equal to h of x plus v. H is my original the matrix that is given to me, that is the m by n. X, please remember, x is a random vector whose mean is m of x, whose covariance is sigma x. V is a random vector which is Gaussian, whose mean is 0, the covariance is sigma v. Now please understand, they are essentially the same except that the mean is a vector, the variance is a covariance matrix. So E of v is 0, V transpose is sigma v, v itself is normal. X is such that the mean of x is m of x, the covariance of x is sigma of x, x is equal to normal. Therefore, h of x depends only on, the h of x is random because of x. So, if you multiply a random variable by a constant, so if x is a random variable with mean m and variance sigma square, if I multiply it by a, the mean is am and the variance is equal to a square sigma square. If you multiply a random quantity by a scalar, the variance gets multiplied by the square of it. You should know. In the case of matrices, instead of square, it becomes h sigma x, h transpose. So the mean is HMF. The covariance matrix is H sigma x H transpose. So if X is Gaussian according to this, HFX is also Gaussian according to that. So this derives its properties from here. Again, I am assuming X and V are uncorrelated. The pathway is essentially the same, except that the algebra is matrix algebra is a little bit more involved. So Z is equal to, so I'm going to look for now Z. So what is that we have now shown? We know the distribution of V, we know the distribution of X, we know the distribution of H of X. X and V are correlated. So sum of Gaussian is Gaussian. The Gaussian sum, the mean is the sum of the mean. The variance is the sum of the variances. The mean of V is 0, therefore the mean of Z is H of Mx. The covariance of Z is Z minus H of Mx times Z minus H of Mx transpose. Please understand, if X is a random vector, the covariance of X is equal to X minus E of X times X minus E of X transpose. That's the definition of covariance of X. I'm sorry, I should write it slightly differently. That is the expected value of this is the covariance of X. So the covariance of X is equal to expected value of the difference, expected of the difference transpose. This is the column, that's a row, that's the matrix, and that's the covariance. Now Z is equal to H of X plus V. So I substitute this. There is a H term common in here, so I can express the first term as H times X minus Mx plus V. This term is exactly the same term, but it's transposed. I have now two terms. I have to multiply both the terms. I get 4 terms. So the 2 terms are in here. This other term is in here. The cross term will vanish because they are uncorrelated. Therefore, the covariance of Z is essentially H sigma X H transpose plus sigma V. So this is the very simple matrix computation that I used the formula for a computation of covariance. I have given all the steps. Please check the steps and verify. Indeed, this is the case. So I have computed the covariance, I have computed the mean, 9 and 8. Now I would like to be able to compute the conditional expectation of Z given X. Conditional expectation of Z given X, Z is Hx plus V. If I am given X, X is known, so this is Hx plus E of that. X and V are correlated, the mean of V is 0, that this is H of X. Likewise, we can verify the conditional covariance is given by VV transpose, which is sigma V. Therefore, Z is Gaussian because it is the sum of 2 Gaussian variables. I know the mean and the covariance. Gaussian random variables have a unique property that if I know the mean and the variance, I know the entire distribution. So this is the mean, this is the covariance. So the conditional. So what is this? This is called the conditional density. So I know the conditional density of Z given X. So I'm just trying to prepare everything, computing all the quantities. The computation of these quantities rely on only few facts. Sum of Gaussian is Gaussian. Sum of 2 independent Gaussian is Gaussian where the means add and the covariance add. That's a simple thing that you can look for. So now what is it involved? Posterior analysis. By applying Bayes' theorem, I get Px given Z. Look at that now. This is the posterior density. It is the information about x after the observation. And that involves the conditional distribution times prior divided by Pz. Now please remember, I have computed each of these quantities. The first example also I computed each of these quantities, they are scalar distribution. Here, distribution over distribution of the random vectors which are vectors. So instead of scalar variables, I just need to be able to manipulate matrix vector. This is more an exercise in matrix algebra. So the numerator is the product of two Gaussian, the denominator is a Gaussian. Now we know the general form of Gaussian density. For example, you should remember that if x is a normal random variable with mean m, with the mean m and variance sigma, its distribution is given by p of x, the functional form 2 pi to the power n by 2. Here I am assuming x is R of n, so this is the general result, exponential minus x minus m transpose sigma inverse x minus m. That is the general formula for multivariate Gaussian density. So I'm going to have to apply this. This is, I would say, n. So if x is a normal random variable with a mean m and covariance matrix sigma, p of x is given by this expression. So this is, okay, I forgot, this is the determinant of sigma to the power half, that's correct. So 2 to the power of n by 2, sigma, determinant of sigma to the power half, the reciprocal of that, times exponential 1/2, this must be minus 1/2 of x minus m transpose sigma inverse x minus m. That is the general form of Gaussian density. I'm going to apply this to each of these terms. So I have all the constant terms. I'm going to club them into alpha. I'm only going to be concerned with the exponents in here. So this is one exponent, this is another exponent, this is another exponent. I hope you are all with me. So consider the expressions in the exponent of the exponential, and look at this now. I can multiply this, I can multiply this, I can multiply this. There are going to be quadratic terms in x, there are going to be linear terms in x, there are terms that does not depend on x. Everything very similar to what we did. This is the quadratic term, this is the linear term, this is the constant term. So this is like ax squared plus bx plus c. I can apply the method of perfecting the square, perfect square. You express as a perfect square. In that process, you define x of ms and sigma e. You remember the same thing that we did in the scalar case. So they are parallel to each other. So if you do the arithmetic and check the expressions for the scalar case, the vector case is also similar. This I can, after perfecting the square, can be written like this, where sigma square e is defined by this and m of s is defined by that. So this is the same as in the previous exercise. So expression 15 is the expression for 14, the exponent, in expressed in the perfect square form, where I have changed the variables. The new variables are x hat ms and sigma square e inverse. So this is this relates to covariance, this relates to the estimate. 16, 17 coming out of 15, and 15 is a simplification of 14. So I have computed the expression for the best Bayesian estimate. So now you can readily see 17 is the quantity that I am really looking for. 17 is the quantity I am really looking for. And 16 and 17 are analogs of 2 and 3. So what is 2 and 3 for scalar? Or 16 and 17 for vector case. So in summary, we have now covered many of the basic principles of statistical estimation. I want you to realize that statistical estimation is a very deep and a broad discipline. There are books written on statistical estimation, very beautiful books. One such book is The Decision and Estimation Theory by Meltzer and Cohen, which I have been referring to all along in these modules. So in summary, what is that we have done? We wanted to introduce the notion of a statistical estimation. We defined what an estimator is. We defined how the estimate comes from. We talked about sampling distribution. We talked about the desired properties of estimate: unbiasedness, efficiency, consistency, sufficiency, relative efficiency. These are the desired properties of estimates. Then we went to analyze statistical least squares. Then we introduced the two frameworks, Fisher's and Bayes. In the Fisher's framework, the unknown is a constant. In the Bayesian framework, the unknown is a random variable. In both the cases, there are observations. In the Fisher's framework, you just have to extract all the information from the observation alone. In the Bayesian framework, I am given two pieces of information, namely prior and the observation. I need to be able to optimally combine them to get the best out of the both. In both the cases, we looked for unbiased estimate, we looked for minimum variance estimate, we looked for blue. And we talked about the similarity between the two approaches. When we did the statistical least squares, we also indulged in a fundamental theorem in estimation theory called Gauss-Markov theorem. Gauss-Markov theorem essentially tells you the least square estimate is a very good estimate. We also saw the Bayesian estimate is a very good estimate. So now you see the different ways to approach. And as an aside, we also saw maximal likelihood approach for the case when I was given only observation rule. So we talked about least squares estimate, maximal likelihood estimate, Bayesian estimate. In each of these things, there is a cost function or a profit function. A profit function is to be maximized, the cost function is to be minimized. So, and there's a reasonably good involvement of properties of matrices in all these computations. So I would like you to go redo, check everything. With that, we come to the end of the topic on statistical estimation. Thank you.